some logistics. This webcast is being recorded, and in order to ensure a clear recording, everyone's phone line has been muted. If you have a question, just type it into the questions section of your GoToWebinar platform on the right. We'll get to all the questions at the end. Just a quick intro about DLT. DLT Solutions helps government agencies or businesses overcome real-world challenges through its broad selection of best-in-class information technology products and superior services available on your procurement vehicle of choice. And then our speaker today is Rick Greenwald. Rick Greenwald is Director of Partner Enablement for Oracle and has been active in the world of IT for more than 25 years. He has spoken on database application development and performance topics across 5 continents and is the principal author of more than 15 books, including Oracle Essentials from O'Reilly & Associates, Professional Oracle Programming from ROX, and the soon-to-be released Archiving Extreme Performance with Oracle Exadata from Oracle Press. So with that, Rick, take it away.
Right, thanks, Trevor. As Trevor mentions, my name is Rick Greenwald. Let me just get clicking here. I am a Director of Partner Enablement, which means I'm responsible for getting all the partner enablement materials. That means classes and tests and knowledge zones and everything you can see as part of the Oracle Partner Network. I've also been fairly involved with Exadata for about the past year. So the presentation I'm doing now is one which I initially gave at a Partner Database Specialist Summit that took place where I am in Scottsdale, Arizona in December. I'm going to be talking about Exadata specifically as it relates to data warehousing. I'm not going to be necessarily talking about all the features of Exadata. I'm not going to be talking about OLTP, although I'd be happy to address questions on either of those topics at the end. But I'm really focusing on how Exadata relates to data warehousing workloads. So we'll talk a little bit about the overall goal of extreme performance, which is delivered by the Exadata database machine. Then we'll talk about hardware, the way the hardware and software are configured, and then reducing resource usage as it applies to data warehousing, retrieving data from storage to database, reducing I/O from disk, and reducing the database CPU workload. We'll end with one customer proof point, although there are many, many others, and then I'll be happy to entertain any questions that you might have. Let's start talking about the overall goal in terms of getting great performance from a data warehousing workload. So data warehousing workloads are distinguished by the fact that they have queries which typically touch a lot of data. The classic example of this is the full table scan, where you have to look at all the rows in a particular table. And the way that we can improve performance is to increase the efficiency of handling that workload. You can increase the efficiency through increasing the resources available to address the particular data warehouse workload, or reducing the demand for those resources. And we'll see both of these things as we go through this presentation. So let's talk about these are the areas we're going to talk about as we go further. We're talking about fast hardware, proper configuration, and something we're not going to spend a lot of time on, but a very important part of the Exadata story is the Exadata database machine is a pre-built box. It comes with all the hardware installed, with the proper configuration, with the software, so you can roll it out and reduce the time to value very significantly. I was talking to some Exadata customers the other day, and they said the time it took them from the time the crates appeared on their loading dock until the time the machine was up and running and operational was less than a day. If you're talking about a very high-end configuration, which Exadata certainly is, that's pretty remarkable. Some customers have said it reduces implementation time by months because of this pre-built nature. In terms of reducing demand, we're going to look at 2 things involving I/O, one of which is reducing the amount of data that has to go from storage to the database CPU. And we do this by means of offload processing, which we'll be talking about quite a bit more later in this presentation. There's also features of Exadata that reduce the amount of disk I/O required to retrieve data from disks, because the overall throughput of the machine is only as fast as its slowest part. And the slowest part in modern computers is the disk I/O, the spinning brown disk. So we reduce the amount of I/O required for that. Something else we'll talk about is reducing the CPU required, because keep in mind, I/O is not an independent operation. It's not that just data flows from storage to the CPU. The CPU has to request that I.O., and then it has to ingest that I.O. So if you reduce the amount of I.O. flowing to the database server, you're also reducing the load on the database CPU. And there are other things which we do at Exadata to reduce that load even more. So let's start by talking about hardware. So this is a basic diagram of an Exadata box. There's a database grid, there's an intelligent storage grid, and an InfiniBand network. The database grid can have up to 8 dual processor database servers or 2 8-processor database servers. Just so you know, in the 8 dual processor servers, those are 6 cores, so you can get up to 96 cores in the box. The 8-processor servers are 8 cores, so you can get up to 128 cores in the box. There's also more memory available with the 8-processor servers. You can also get smaller configurations with 4 dual processor servers or 2 dual processor servers, we call a half rack or a quarter rack. The intelligent storage grid in a full rack has 14 high-performance storage servers. Those storage servers include disks, 12 disks per server. It includes memory and CPU for the processing, which I'll be talking about. And it includes some flash storage, which we use for flash cache. We're not going to talk a lot about that because that's primarily relevant to OLTP, but we'll mention it in passing. Keep in mind, though, that each storage cell has all 3 of those things. By the way, a storage cell can either have high-performance SAS disk for 100 terabytes of raw space or high capacity with 336 terabytes of raw space. Also, very importantly, we use InfiniBand to connect the storage grid to the database grid. This is very high bandwidth, so you're not really going to get any slowdown in the transmission of data from the storage server to the database server. It's all balanced. That's the whole idea here. The balanced configuration means you're not going to run into bottlenecks at any point in the overall data flow. What I talked about is our current release, what we call our X22 and X28 servers. But Exadata hardware is periodically refreshed. Just so you know, Exadata has been out there for a little more than 2 years, and we've had 3 refreshes already. In the last refresh, we went from what were 2 database servers two processors in each database server, and each one of these had 4 cores. Now we have 6 cores in the X22 configuration and 8 cores in the X28 configuration. We've also added more memory on the X28 configuration. We have 2 terabytes of memory on the 2 database servers, 1 terabyte per server. About 768 gigabytes of memory if you're going for the X22 configuration with the full rack. We've also added more capabilities as the hardware advances. So for instance, we have new chips in the database server and the storage server, and these chips support a firmware capability to do decryption. So this means you can now do all the decryption in the actual chip itself, reducing the CPU cycles required for that. You can actually encrypt using that on the database server also. So the basic thing here is, as hardware advances, as chips get updated, as more capabilities come in, we add that into subsequent releases of the Exadata database machine, and we do it pretty rapidly. The configuration is very important because, of course, your overall performance is going to be determined by bottlenecks, not by overall capacity. So if you don't have a balanced configuration, you'll introduce a bottleneck at some point. You can have the fastest CPUs and the fastest disk in the world, for instance. At the transmission level, if you're using fiber channel or a lower bandwidth connection, it doesn't make any difference. You're only going to go as fast as the slowest component. We create Exadata database machines with an optimal configuration. So this means we max out the memory in the database nodes for SGA, because the absolute fastest retrieval of data is from the SGA. So the more cache you have in your data buffers, the better you're going to be doing in the database server. We also balance the memory specification for the SGA and the PGA appropriately. We've done this through testing with customers as well as our own calculations. The InfiniBand provides maximum bandwidth for data transfer, so this will not be a bottleneck. we really haven't seen this at all, that we get throttled by the transmission from the storage server to the CPU. Each storage cell has 12 disks, so it implements parallelism across those disks, and that's done through Exadata software and through automatic storage management, ASM, which is what we use to handle volume management on the Exadata database machine. Of course, if you have 14 cells in a full configuration, that's 168 disks spread out, so very high degree of parallelism there in disk activity. Also, we do some CPU processing on the storage server. We'll talk a lot more about that in subsequent slides. It's important to understand that we have a balanced configuration, because if you have a configuration where you have servers and you need more storage and you buy more storage, all you're doing is you might be increasing the I/O capacity of the servers, but if your database CPUs are maxed out, it's not going to make any difference because they can't get the free CPU cycles to ingest the additional data. So we have balanced configurations. In a full rack, let's say X22, a full rack will have 8 nodes for database servers, 2 processors per node, and 14 cells. And a half rack will have 4 nodes and 7 cells, and so on and so forth. So as we increase the I/O bandwidth from the storage cells, we increase the database servers to take advantage of that. There's also memory on each node to allow for increased caching, and each storage cell has CPUs, flash, and disks. So as I/O increases with the cells, the additional resources required to take advantage of that I/O is also increased. And of course, the InfiniBand interconnect has a broad bandwidth, so it allows for scaling across not only multiple cells, but you can use InfiniBand to interconnect between different full racks. So you can actually expand out to up to 8 full racks and still have that bandwidth balanced across those racks. So that was talking about capacity. What do we have and how do we implement the hardware resources used in the Exadata database machine? How do we make it more efficient? By reducing the demand on those resources, increasing efficiency by reducing demand. And the first thing we'll talk about is reducing data sent from storage to the database. So the problem is fairly straightforward. The greatest overhead in terms of I/O is when we're doing a full table scan. And if you've been in the database world for a while, you probably learned to avoid full table scans, because a full table scan will return all the data from a table to the database server. This means a lot of disk activity. It means a lot of network activity or bus activity moving from the storage server to the database servers. And it means a lot of processing activity on the database server as it has to ingest all of that data and make a decision frequently based on selection criteria or join conditions. The greatest benefit can come from reducing sending unnecessary data, because it means we don't stress the bandwidth between the storage server and the database server, and we don't use up the CPU on the server just going through data to throw it away. And so what we've done with the Exadata database machine is to implement something we call Smart Scan. And to understand Smart Scan, it's best to walk through what happens with a normal full table scan and then look at how that's implemented with Smart Scan. So in a normal full table scan, this is what happens. You have a selection statement, you have a select statement. The optimizer decides that a full table scan is the best way to get the data. So the optimizer says you're going to have to get all that data in the complete table. The table extents required are identified, the IOs are issued, the IOs are executed. So if it's a terabyte table, you're going to get 1 terabyte of data, which is retrieved from disk and then sent to the database server CPUs. Those database server CPUs then go through all of that data, throw out the data that isn't necessary, throw out the columns that aren't necessary, and return the rows to the user. So we can see that from step 2 to step 5, there's a lot of unnecessary data going along for the ride, consuming a lot of resources. With Smart Scan, it works a little bit differently. Same SQL statement. The extents are identified, and the extents are sent to the storage server along with metadata. So things like, is there a selection criteria, is there going to be a join? And there's intelligence in the software on the Exadata storage server. And it uses that metadata to, for instance, identify the rows which need to be sent back and the columns that need to be sent back. So it may read the whole terabyte data, still do the I/O on disk, but is only going to send back 2 megabytes of data. That 2 megabytes of data will be processed by the database servers, but of course it's much less CPU overhead on the database server, and then the rows are returned to the end user. There are a couple things to point out here. The first is that from the way that application or the end user interacts with the Oracle database, there's no difference at all. It's a select statement. It's the same select statement. Nothing is different. This will work transparently with any application you have. There's another thing which is really important to understand, which actually has pretty profound implications. If I were in a room with you now, I'd ask, how many people have added indexes to their tables to improve performance and avoid full table scans? And typically, everyone's hand goes up. We find that frequently, most of the indexes on a database are there to improve performance and avoid full table scans. Well, what you will see with Exadata and what our customers have seen is that with Exadata, a full table scan is really, really fast because of Smart Scan and other features I'll tell you about. So consequently, if the only purpose of an index is to improve performance, you can get rid of it. And we find it's not unusual for people to get rid of between 70 and 90% of their indexes because they're not serving any useful purpose anymore. They're getting the performance they need without the index. There is both a space implication of using indexes and a maintenance and a workload implication because when you update data or load data, you have to do the same thing on the indexes. So this is also a pretty big deal. The fact that you can get rid of a ton of indexes which are no longer needed to provide good performance. So what's done in a Smart Scan? There's two basic things that are done. One of which is what we call predicate filtering. Predicate filtering says, I've got a where clause, and here's all the relational operators that you can use in a where clause. You can also use most SQL functions, and the Exadata storage server software will take that predicate and apply it to the data on the storage server to eliminate rows which are not appropriate to be sent back to the database server, which will not be needed. I say most SQL functions. You can do this SQL statement here to find out exactly which functions can be offloaded. It's most of them. Of course, we want it to be all of them where we can. We also do something called column projection. And what that means is if you have a select statement that says select B and C from table A, it's only going to send you back those columns required. By the way, that's not an absolute rule. It's going to send back the columns required to process the remainder of the query. So there may be other columns that could be used for a join or a sum or something, which are going to be sent back. But the basic fact is that if there are columns which are not necessary, they will not be returned, which reduces the amount of I/O sent back even more. The last thing that we use Smart Scan for is something called join filtering. It's particularly appropriate in terms of star schemas. And let me just explain how this works. A join, really, you can look at it as a dynamic where clause. You have two different rows together. You want to join them together, and you say where column in this table equals the column in that table. What we do with join filtering is, when appropriate, we create what's called a Bloom filter. And a Bloom filter is basically a way of building a list of values in a very compact space. So you take this list of values and use that as the target of an in clause. So essentially, if you have 1,000 rows with 1,000 different values that could be used in a join, those 1,000 values will be reduced in size into a Bloom filter, sent as part of the metadata to the Exadata storage server, and it will use that predicate and apply that predicate on the Exadata storage server. Now, by the way, a Bloom filter is an interesting piece of technology, which, by the way, we use this in the Oracle database too. We use this outside of Exadata also. But a Bloom filter has a very unique quality. It reduces the space required for information, but of course, whenever you do that, you're going to lose some information. But a Bloom filter is mathematically guaranteed to never produce a false negative. What that means is it may produce false positives, but not false negatives. So it may return rows for a join, which won't be used in the join. But it will never eliminate a row that might be used in the join. This is exactly what we want when we're cutting down the rows which are going to be sent back. Because, of course, if there's a row that can be used for a join, for data integrity purposes, it has to be sent back. Because if you have a join and there's an option for the join, the driving table row is thrown away. You can't do that. But Bloom filters don't do that, so they work very, very well in this scenario. A little bit about the way smart scans work. When you look at an explain plan for a particular query, you'll see that it will indicate execution plan steps that qualify for smart scan. And that means full table, I think it's full table storage scan or full index storage scan. What this means is that this step in query execution can be used for a smart scan. It won't necessarily be used because the storage server will make that final determination. If it's a small table, if there are a number of other environmental conditions, it may not do a smart scan, but it might. If you want to see if a smart scan was actually done, you can look at the $SQL view in order to get statistics, and there are statistics in there which will tell you the effectiveness of the smart scan itself. One other way that offloading processing to the Exadata storage server software eliminates data sent from storage to the database is in reducing the granularity of backup data. You're probably all aware that RMAN can do block change tracking. What this means is that when you're doing an incremental backup, RMAN will only back up the blocks which contain changed data. It won't be the entire table that's changed, it's only the blocks that have changed. Now, block change tracking is a feature of RMAN, which is a feature of the 11G version of the Oracle database. It works the exact same way with Exadata that it does with the normal database. The difference is that with Exadata, Exadata itself tracks the individual blocks which have changed. So without Exadata, RMAN will say, I need to get this block. And the storage system will return a number of blocks. I think it might be 4, but it's more than one block will be returned. With Exadata, the identification of that block is offloaded to the storage server, so if RMAN says this block has changed, it will only return that block. So less I/O to the database nodes using block change tracking with RMAN. More efficient backup. So that's how we reduce the amount of data being sent from the Exadata storage server to the database nodes in the Exadata database machine. There's also ways that we can reduce I/O operations going to disk, because of course the fastest I/O is one which you never do. So Exadata is really fast. There's up to 168 disks. They operate in parallel. They're very quickly spinning, but you're always going to reach a finite limit. Physical action, so there's only so many I/Os you can do. So if you can reduce the number of I/O operations, you can basically increase effective throughput. What effective throughput means is, if you go back to the example we saw before, if you have a 1 terabyte table, the effective throughput is 1 terabyte to read that table. If in fact you can cut down the number of I/Os you do to read that 1 terabyte, then in fact you're going to increase the throughput with the same number of I/O operations. One main way that we do this with Exadata is something called a storage index. Now, a storage index is pretty cool. It's pretty magical. A storage index works in many ways like a mini partition. What that means is that Exadata tracks what are called storage regions. And a storage region is 1 megabyte. And it tracks the values of data in those storage regions. It tracks the maximum and minimum value for columns kept in that storage region. What that means is every 1 megabyte storage region will have a number of values, the different columns in that storage region, the minimum and the maximum value. When a SmartScan query comes in, be it for a join or for where there's a predicate available, the Exadata storage server software looks at the minimum and maximum and says, you know what? Let's take this as an example. You're going to say where B is greater than 6. If you look here, the first block says the maximum value is 5 in this block. I know that no row in this block can satisfy this query, so I won't even retrieve that block. The same thing could happen if you say select from the table where B is less than 2. You already know the minimum value in the second block is 3. So the Exadata storage index knows not to retrieve that block. Essentially what you're doing is you have a mini partition 1 megabyte in size automatically implemented. A couple things important to know about the storage index is it's very important to understand your query never runs slower because of the storage index. It may not benefit, but it never runs slower. The other thing to understand is that there are certain use cases which really benefit from storage indexes. And here's a classic one. As you know, when you partition, your primary partition has to be on a single column. So let's say you have a scenario where you have order number, order date, and ship date. You can only put a partition on one of those values, but they increment in step. In other words, as the order number increases, the order date increases, or rather, excuse me, as the order date increases, the order number increases, but they increase in the same direction. The ship date also increases, although not necessarily in the same direction because there's more variability. But let's say you decide to partition on order number, and you come up with a statement that says select where order date. Well, you're not going to use that partition at all. That partition only applies to order number, even though the range of order dates in a range of order numbers is matching. So the storage index will give you a way to automatically eliminate those matching, those values which increase along with the partition key, and it will work out fine that way. I apologize. I work for my home office. That's my home phone, but I'll just keep going. So that's when storage indexes can be very useful. And of course, if you're loading data into the database server, you might want to load data which is sorted, which will reduce the spread of values within a storage region. So a little bit more than is on the slides, but storage indexes in certain scenarios can be incredibly powerful and increase value. It reduces the throughput enormously. Sorry, increase effective throughput, reduce actual I/O operations. A little bit of use information. Storage indexes are created as a result of a SmartScan query. So this means, let's say you're booting up your database machine, there's nothing in memory, because the storage index is kept in memory. So when you reboot a cell, you lose the storage index. The first time a SmartScan query comes through and touches a block, the storage index values are computed, and then they're replenished, are computed. Sorry, the first time you touch them. And then the next time there's a query that needs the same storage regions, it will use them. There's some heuristic calculations built into the software. So we don't keep values for all the columns, but we do track how often those columns are being used in the SmartScan to eliminate I/O. So slowly, as more SmartScans go against data, we'll drop the columns where there's a very broad range of values and they're not really helping to eliminate I/O, and we'll end up with the columns which contribute the most to the performance improvement that you get with storage indexes. And as I mentioned, loading data in sorted order can increase the effectiveness of those storage indexes. Another key feature of the Exadata storage server, which can reduce the amount of I/O from disk, is the Exadata hybrid columnar compression. We've had compression in the Oracle database for a long time. It's been, 10, 15 years. We introduced advanced compression with, I believe, 11G, but Exadata hybrid columnar compression is completely different. As the name implies, the compression is based around a different organization of data. We organize data not by rows, but by columns. So we have something called a compression unit, and it's multiple blocks. And when you're loading data, all the values for one particular column are stored together, then all the values for another column, and all the values for another column. So we get column values stored together in close proximity. The second thing that we do is we have different algorithms for compressing different data types as appropriate. So you can have different data types in a single table that were compressed with different algorithms for maximum effectiveness. As I mentioned, the compression only is implemented when you're doing a direct load. So if you're doing periodic updates, those rows will be decompressed, stored in a different compression format, and not recompressed. But the bottom line is you get really dramatic compression improvements. So we have two modes, query mode and archival mode. With query mode, you should see queries running just as fast, if not faster, as you would with decompressed data. The reason it runs faster is there is some overhead for decompression, but the fact of the matter is if you have a 5 or 10x compression ratio, you're doing 1/5 or 1/10 the number of IOs. And we consistently see that with compressed data, you get faster query performance in query mode. Archival mode will give you a better compression ratio, and we have seen 50, even 70-fold reduction in size. But there may be a performance impact when you're running queries against these. But the whole point here is that archive mode means this is data which you're not going to access very frequently. As a matter of fact, this may be data which you would back up to tape and not use. So number one, now it's available, even if it's a little slower. Number two, you save on storage. If it's 5 times, 10 times, 20 times compression, you use that much less storage. And really importantly, you not only save on storage, the data remains compressed when you do backup. The data remains compressed when you're using data guard and moving over to a standby machine. The data remains compressed in the cache. So all of these things, the benefits flow through. So keep in mind what this means with something like Smart Flash Cache. You can have up to 5 terabytes of data in a full rack in Smart Flash Cache. Well, if you're getting a 10-fold compression, this means you could actually store effectively a 50 terabyte database in Flash Cache. Actually 40 terabytes, but still a pretty large database stored directly in Flash Cache for really rapid performance. So the one thing I didn't mention here is the hybrid capabilities. There are other databases out there that store data by columns, and they can do columnar compression, but they have a problem. They'll store all the values for one column in an entire table together. So if you're doing a single row lookup and reconstructing that row, you're going to have to do an awful lot of decompression to get to that data. We only store a fixed number of rows in a compression unit, so we avoid that problem. So we provide good performance across the board for all types of operations. As I mentioned, when you update a row or when you write a row to a table space with hybrid columnar compression, that row is not stored with hybrid columnar compression. It's stored in another compression format. And this last thing is very important. As I mentioned, a compression unit holds multiple rows. When you do an update of a row in a compression unit, the entire compression unit is locked. So a lock will be preventing write access to rows which are not being updated. And hopefully everyone out there understands Oracle and understands why we stopped doing this years ago. This is a really bad thing to do. So the bottom line here is Exadata hybrid columnar compression is a great feature, can save you money, can improve performance, but you really only want to do that with read-only data or read-mainly data. You don't want to use this for OLTP. You don't want to use this for data exchange. Oh, by the way, you can implement hybrid columnar compression by doing an alter table move or an alter partition move, and that will implement it again. and get everything back in that format, but that, of course, uses resources itself. So there's been some discussion on some forums about whether you can use this for OLTP, but it's just not a good idea. It varies from not a good idea to a really bad idea. So this talk is about data warehousing. I can say that hybrid columnar compression for data warehousing, great, without any hesitation. The last thing to mention in terms of reducing I/O from disk is the Exadata Smart Flash Cache. This is the flash storage which is included in each storage cells, and of course it has a much greater bandwidth than retrieving from disk. Exadata software is smart enough so that if you're doing a full table scan and some of the blocks of that table are in flash cache and some are on disk, it will actually hit both of them. So you get the aggregate bandwidth both from disk and from flash cache together. Only the results of small I/O operations are kept in Smart Flash Cache by default. Same way that the data buffer cache works. This is what you want. You don't want to be doing a full table scan normally and having that full table scan knock out all the other blocks. So it works best with small I/Os. Now you can pin a table in the flash cache. You can say, I want this table to be stored all the time in flash cache, and it will be kept there. As soon as you read it, it goes in the flash cache and it stays there. It actually can get aged out of the cache, but it's aged out with a different algorithm, so it's typically going to be there all the time. The one limitation is only 80% of the available flash cache can be used for tables pinned there. So you can do this. You know your usage patterns. You can tell whether this is something you should do or not. But remember, it's typically not what we recommend for a very simple reason. It's going to require more management. Because remember, if you pin a table in flash cache, you want it to be there all the time. You don't want it to be there part of the time. You want it to be there all the time, right? So if your table grows, and now the total amount of storage required from your table or tables pinned in the flash cache is greater than 80% of available cache, some of that data won't be available. So you'll certainly be undercutting the advantage of the flash cache, not destroying it, but still you're not going to know whether it's there in the flash cache or not. The other thing is, it's like a data buffer cache. We are very smart. There's a lot of intelligence built into how we cache stuff. So if there's really a block which is being used a lot, typically it's going to be in flash cache already, and it does it automatically with no additional management overhead. So it's been kind of a high-level fly-through of the features available in Exadata database machine for data warehousing, but I want to close out by talking a little bit about a particular customer of ours and the sort of improvement they got. Real-world improvement. This is not in the lab. This is not a benchmark. This is a customer, okay? It's a, I'm sorry. I had one more thing to mention. Forgive me. I'm reading ahead of my slide notes. You can also reduce database server CPU workload because keep in mind, Smart Scan and join filtering are reducing the amount of processing that has to be done by the CPUs by sending less data there. It's also offloading the processing to the CPUs in the storage cells. So it offloads processing for join filtering, for Smart Scan, and a few other things. Data mining scoring. I don't know if you're using data mining, but if you are, you know that data mining works by setting up a condition where different rows are scored to see how well they fit a particular model. This scoring can be a fairly CPU-intensive operation, but that's completely offloaded to the Exadata storage server. As I mentioned earlier, decryption can be done by the CPUs in the Exadata storage server. In the latest release can be done by firmware in the Exadata storage server CPUs. And the last thing is actually pretty important. Whenever you allocate new extents, either by creating table space or extending table spaces, those extents have to be initialized. What that means is the Oracle database has to write to every block in that new storage space. That block initialization is offloaded to the CPUs in the Exadata storage server. So these operations, which can have an actual noticeable impact on performance in different times, are now almost instantaneous because metadata is sent to the storage server, control is returned back to the database server, and the initialization is done by the CPUs in the Exadata storage service. So when you're reducing the load on the CPUs in the database nodes, this means more of their cycles can be used to ingest data. So this also improves overall I/O throughput by reducing the load on the CPUs in the database. Now I'll move on to the customer through point I was mentioning earlier. So this is a large customer. Frankly, it's one of the largest databases in the world. They're a large telecom operator in a country in Europe. They have 60 million customers worldwide. These are large databases they're talking about. Their largest database was 250 terabytes, which was reduced to about 100 terabytes with compression. It was on 2. It was migrated to a database machine version 2. It's now about 25 terabytes DHCC. So this is a pretty big reduction. They run over 50,000 reports every month, and the performance improvements average tenfold. Some of the reports go up to 400 times. See some exact reports, some exact figures in the next slide. But, you know, keep in mind, think about this just for a second. Database is a really established technology. The Oracle database has been out there a long time. We have thousands of users. When was the last time you heard of a new release of a product that gave you a tenfold improvement in performance? So here are some of the actual reports and the improvements they got. There's a few things to note here. Different improvement for different type of reports. Depends on how much these different reports can take advantage of the various features in the Exadata hardware and software. So you can see there's a control report that went a little more than 2 times faster, actually almost 3 times faster. Some reports go way faster. I mean, you can see the BlackBerry report went from 3 minutes and 20 seconds to less than a second. But the report I want to point out here, which is most interesting to me, is the prepaid report. It used to take 8 hours, and now it takes under 2. So, of course, that's a batch report, production level report. It took a long time to run before. It still takes a while to run. But keep in mind the sort of impact this can have on your business operations. The report takes 8 hours to run. How often are you going to run it? One time, night. How old is your data going to be? Could be 16 hours old. If it takes less than 2 hours to run, you can run it multiple times during the day. So this can have a dramatic impact on how you actually run your business. IT contributing to increased business flexibility and higher revenue possibilities. This is a big win. This is very cool. So that's basically what I just talked about. One last thing to note, which I'm going to talk about a different company, Giant Eagle, which is a large food chain in the eastern United States. They experienced performance gains, but they said something which I think was even more impressive. They were able to do, because of the increased performance, they were able to go to an extended level of analysis, which resulted in quantifiable cost savings that paid for their Exadata database machine in 9 months. That's pretty good. So that's the end of the main part of this presentation. If you're interested in Exadata, I have a recommendation for you. Excellent book coming out. Actually, the title's been changed. It's called Achieving Extreme Performance with Oracle Exadata. And I'm going to do something now which no one else has ever experienced. Listen to this. Hear that? That's the book. Okay. This morning, a box of these books arrived on my doorstep. I think it's a pretty good book. It is obviously currently available because I have one in my hot little hands. You can order it from Amazon, and I encourage you to get it. I'm actually pretty happy with it. One thing that you may have experienced about Exadata already, which you may have found out from coming to this presentation, is there's a lot of stuff about Exadata which is known but not very well exposed or documented. When I was writing this book, I had an experience over and over again, the same experience, which was I'd come to something, I would have a partial understanding or I think it was magic, and when I went through actually understanding it, I found out it wasn't magic, but actually it was really, really cool. And there's a ton of that stuff in this book, along with a lot of information about best practices for maintenance and using Exadata data warehouses and OLTP and consolidation, and migrating to the Exadata database machine. So with that, Trevor, I'll ask if there are any questions.
All right, thanks, Rick. I'm not seeing any questions come in, but again, if anyone has any questions, I'll give you a couple seconds to type one in and send it over. Want to thank
Rick, should do that chat?
Yeah, on the question feature on the right side of the screen. But in the meantime, I just want to thank Rick for presenting today. I'm sure that was pretty beneficial for everyone. And just to let everyone know, we did record today's webcast, so you should be seeing an email in the next couple of days with information how to access that, and you'll be able to share that with other people if you need to. So Rick, I'm not seeing any questions come in, so I think that will wrap it up for today. I'd like to thank everyone for attending again. So thanks, everyone. Be on the lookout for archive information. Thanks.
Thank you.